Hello friends, welcome to Unacademy. Crack GATE Computer Science with us, top educators, quality content, great learning experience. Let's crack GATE CSE. Our anthem is Crack GATE and ESE with India's largest learning platform, none other than Unacademy. Get Plus subscription and access unlimited live and recorded courses from India's topmost educators. Myself is Srinivasarao Sir, having 17 years of GATE experience in the areas of DBMS, CN, and operating system. Also had industry experience as a database admin and a system admin. Also had certifications in DBA, Cisco, Microsoft, and Red Hat Linux. All my GATE journey, I taught in many premium academies, including MEDIZI, GATE Forum, the GATE Academy, and many others, with high success rate, which including single-digit rank of AIR. Please subscribe to Unacademy. Let's crack GATE CSE. Once you get the subscription, what will you get? You will get daily live classes and where you can able to discuss with your concerned faculty members and clear your doubt session. We all know that live test and quizzes and mock test played a very important role in real-time examination. Unacademy also provides detailed analysis and live test. It also provides structured courses which are predefined as per the syllabi of respective competitive examination. Once you get the subscribe, then you will get unlimited access to your courses, recorded lectures, and live lectures. As far as CS and IT concern, there are many courses are available. Once you get subscribed, you are allowed to view them. There are two kinds of subscriptions are there. One is 12-month subscription and the other one 24-month subscription. If you apply my promo code Sankara, then you will get 10% off. So which is costing 12 months is costing around 22,500 and 24 months is costing around 27,000. Subscribe to us, learn quality content from quality topmost India's educators. As far as DBMS subject concerned, here I am going to present full course of DBMS on behalf of Unacademy. This is the schedule. An evening class I am doing with special classes on student learning gap, which is mainly focusing on to MCQs and PYQs with the detailed explanation. Now today we are going to discuss about the very important property, that is lossless join and dependency preservation, as the continuation of last session. In last session we were learning about lossless join, that is theorem 1 and theorem 2 we completed. Today we are going to look into theorem 3, that is lossless join, which is very mostly used in examination as it is used as a shortcut to solve lossy join and lossless join. And the other important property is dependency preservation. We are also going to discuss about it. So why we are learning the lossless join property and decomposition property and dependency preservation property? Because the main objective of decomposition is nothing but it is mainly used in conversion of lower level normal forms to upper level normal forms in order to avoid a concept of redundancy. So redundancy damages the database like anything because it provides further inconsistency and data dependency problems. To avoid these problems, there is a requirement of decomposition. It is nothing but divide a large relation into smaller relations. There are mainly three properties we are going to check whether decomposition is best or not. Why are we doing decomposition? What is the main intensity of the decomposition? These are the problems. What are the problems, friends? There may be a chance of redundancy, or maybe a chance of inconsistency, or maybe a chance of data dependency problems, or maybe a chance of anomalies problems. In order to avoid any of these problems, there is a mandatory requirement of decomposition. Decomposition is going to avoid all these problems and you will find 100% perfect database. As far as last lecture concerned, we performed some of the examples on attribute preservation and theorem 1 and theorem 2 as far as lossless join concerned. Today we are going to discuss about the theorem 3 and the very other important property called dependency preservation. So what is the theorem 3? Let us check. The theorem 3 is mainly focusing on it is eligible for any number of decompositions. This is the advantage. It is eligible for any number of decompositions. It is not mandatory as like the last session, it is applicable only to two decompositions. You want to merge multiple decomposition, it is not possible with theorem 2 in a simple manner because the theorem 2 is saying that you can combine two decompositions at a time, then take that result and merge with other decomposition. But the theorem 3 is saying in such a way it is eligible for any kind of decompositions. What the theorem 3 is talking about, few important rules. The rule number 1 is write all the attributes of given relation and the second one, write decompositions. That means we are going to write the given attributes as a columns and the decompositions we are going to mention as a rows. Now what is the third important rule is we start to apply all given functional dependencies to check it is deriving R. So what is the rule? In order to apply the functional dependency, the rule is, this is the rule to apply functional dependency. What is the rule is LHS, which we are calling it as a determinant, must be common in any of the two decompositions, in any of the two or more decompositions. This is a rule in order to apply any functional dependencies. Well friends, let us look at into one small example using that. The example is saying like this: there is a R which consists of ABCD with the functional dependencies as A tends to B and B tends to C and C tends to D, and the decompositions given as AB and BCD. If you assume, now he is asking, check whether it is LLJ or LJ. As I told you, the three important steps. The three important steps are like this. First, write all your given columns. There are 4 columns are given, and you post the decompositions now. There are 2 decompositions, namely R1. Write them as tuples and mark them if at all they appear in the respective attributes. Here, the decomposition R1 is marked as it is AB attributes, and decomposition R2 is being marked especially in BCD as it is decomposed with 3 attributes. Now we start doing applying functional dependencies such as A tends to B. So how to apply the functional dependency? As I told you the rule. What is the rule? To apply the functional dependency, LHS or a determinant must be common. Therefore, using that rule, you see that could I able to apply A tends to B or not? As far as this concern, A is a LHS and A is not a common in between R1 and R2. Therefore, I cannot apply A tends to B. Let us check for B tends to C. As it is a common, wherever it is a common, then I can able to fill its dependent value, that is C. Now I am marking with C here. Now this is done. Now I am looking into C tends to D. Wherever the C is a common, you can apply D. And after applying functional dependencies, you need to check whether any particular decomposition is marked with the corresponding symbols. Therefore, R1 itself is giving all the columns of your original R, which is implying R. This condition is satisfied that it is lossless join. Well friends, it's a very simple to apply 3 steps. The first step is apply all your attributes in a table format. Write your decompositions as rows. Mark them in respective position, like in the first AB is decomposed. In the second, BCD is decomposed. After that, I am applying functional dependencies. So A tends to B cannot be applied, but B tends to C is possible to apply, and C tends to D is possible to apply. And after applying some functional dependencies on this, you got derived the original relation R, and it is LLJ. This is an idea. Now, if I am taking another example here, the example is like this. This time there is ABCD with the functional dependencies such that AB tends to C and C tends to D. Now the decompositions are mentioned as AB, and the second decomposition is BC, and third decomposition is CD. Now let us go for solution. What the solution is, write your 4 attributes which are given in the relation and post your decomposition R1, R2 and R3. So mark them as R1 is marked with AB and R2 marked with BC and R3 marked with CD. Now you check, can I able to apply AB tends to C functional dependency? It is not possible to apply AB tends to C because the AB is not common either in between R1 R2 or between R2 R3 or between R1 R3. Henceforth, we cannot apply AB tends to C functional dependency right now on the current table. Now I am moving on to C tends to D now. What the C tends to D is saying, is there any common? Yes, of course there is a common between R2 and R3. Now you see that wherever C is available, I can able to fill the D value. Therefore, the C implies D here and mark. So after marking, this is done. Now we are going to check with AB tends to C once again. But here we cannot apply AB tends to C still because the determinant LHS is not a common in this. Hence, this is not possible to apply on the current working relation. Therefore, after applying all the functional dependencies, we are going to check any of the row is giving you R or not. So we understand none of the rows are giving you R, hence it is called as what? Lossy join. Very simple friends, to prove lossy and lossless join using theorem 3. Need not worry about theorem 2, it is very easy to solve it. Now, so what the lossless join is talking? Lossless join is talking that data must not lose, also called as dependencies also must not lose. Dependencies must not lose. This is the idea behind lossless join. In order to prove this, I taught you 3 theorems, theorem 1 and theorem 2 and theorem 3, and this you have to merge 2 decompositions at a time. You have to merge 2 decompositions at a time. So it is not possible to merge multiple decompositions at a time. So in order to do multiple decompositions at a time, you're supposed to use the theorem 3. So the theorem 3 is for multiple decompositions. Well friends, now using theorem 3, let us start working on some examples. What are the examples are there? Let us see the first example. There are 5 attributes in the R, namely A, and B and C and D and E. Now you post the decompositions, the decomposition R1 and decomposition R2 having some attribute sets. So the first decomposition is with ABC, second decomposition is with BCDE. So finally, we want to apply the functional dependencies. I am applying first functional dependency, that is A tends to B. I cannot apply A tends to B here as A is not a common. A is not a common in R1 and R2. Hence, I cannot apply A tends to B here. Now, let us go for A tends to C is possible or not. It is also not possible as A is not a common in that. Now, we will work on to DE tends to C. What is DE tends to C? DE is a determinant and that determinant is not common in between R1 and R2. Hence, this is also not possible to apply. So, DE tends to B. Is it possible to apply? Again, you need to see that the DE is not common either in R1 or in R2. Therefore, you cannot apply DE tends to B. Now, let us see that C tends to D is possible or not. Yes, of course it is possible. Why? The C is a common between R1 and R2. Wherever the C is a common, I can fill a D value. Now I am filling D value here. After filling it, this is successfully applied. Let us go back and verify anything is possible to apply or not. As far as this concern, A to B is not possible to apply and A to C is not possible to apply and DE to C, DE is a not common, not possible to apply and not possible to apply. After applying all these functional dependencies, we come to know that this is not giving you R and this is not giving you R. Hence, we will prove that it is a what, friends? Lossy join. Because after finding out all the functional dependencies, we understood that some of the functional dependencies we are unable to apply there, and that too, none of the rows are returning your R, and it comes under into lossy join. Okay, friends. Now let us move on to one more example. This is given with two decompositions. There are 5 attributes, namely A, B, C, D, E, and few decompositions like R1 and R2. The first decomposition is a mention as ABC. We will post that ABC in the first decomposition. ABC is applied and the second decomposition is CDE is applied. Now we start apply the functional dependencies. What are the functional dependencies I can apply? A to B I can apply, but A is not a common to apply it. Therefore, readily you cannot apply A tends to B. Is it possible to apply A tends to C? Not possible as A is not a common in that. Then is it possible to apply D to C? Let us check. D is not a common between R1 and R2 and it is also not possible to apply. And is it possible to apply D to E? Not possible. After applying, none of the rows are giving you R. Hence, we confirm this is also what? lossy join. Now we will move on to one more. So these are all the examples which I am working on theorem 3. That is a shortcut in the examination we can apply easily. Now there are 5 attributes in this, namely and there are 3 decompositions R1, R2 and R3. You post the data. R1 decomposition is ABC, R2 is BCD, R3 is CDE. Now you apply functional dependency AB tends to CD. Right now we cannot apply AB tends to CD as AB is not a common in R1, R2 or R1, R3 or R2, R3. Now we will move on to second decomposition, that is A to E. So since A is not a common between them, I cannot apply E also. So let us try to apply C tends to D. As C is a common in all the 3 decompositions, wherever it is a common, you try to apply its dependent. What is its dependent? D. After applying, still we have got some vacant positions which is not giving you R and which is not giving you R and this is not giving you R. Hence, we will call this is what? Lossy join. The number of examples I am providing you to prove that it is a lossy join, not lossless. Now, we will go for one more example. There are 5 attributes, namely A, B, C, D, E, and 2 decompositions R1 and R2. R1 is ABC, R2 is ADE. Now we start apply the functional dependencies. The first functional dependency is A to BC. Now you observe carefully. As A is a common, I can apply B value as well as I can apply C value, but you need not check the remaining dependencies. Why? Because it is giving you R. Hence, we will call that it is a what? A lossless join. Okay, friends. Now let us check another one using dependency preservation. This is the last important property to prove that decomposition is best or not. What the dependency preservation is telling that all the given dependencies, of given relation must exist in the subrelations. This is an idea how you could able to prove dependency preservation. There is a rule such that F plus is nothing but given functional dependencies closures, given functional dependencies closures, and G plus we are going to compute such that functional dependencies of decomposed tables What you need to prove that the proof is like this. That means the G plus is equal to F plus. In such case, it is dependency preservation. Now you see, if G plus is superset to your F plus, then we will understand that all these functional dependencies are implied by G, hence I will put that it is also dependency preserved. In other case, that if G plus subset to your F plus, which means some of the dependencies are lost. Some of the dependencies are lost, and this rule is telling you that it is not dependency preserving. So what is G here? The functional dependencies of subrelations. What is a F here? The functional dependencies of given original relation. So if these may be one of your 1 mark GATE questions by asking these rules. So using these rules, you can easily answer that if both are equal, then DP, even decomposite tables might have got more dependencies than F, no problem. But you see that all these functional dependencies of F must be written by G, otherwise it is not DP. This is an idea. So using that, we are going to solve some of the problems using dependency preservation property. The first one is like this: R on AB, R2, BC is given. And the given functional dependencies are here. F, we want to find the closures for them. The F closures are, please observe carefully, A to B, union, B to A, union, A to C. These are the F dependencies. Now what are the G dependencies? The G dependencies are AB closure, union, BC closure. So you need to identify few of the functional dependencies on AB and BC too. So as far as this, I can get A closure and a B closure and AB closure, union. Here you can get B closure, C closure and BC closure. If you have any doubts, please put in the comment. You can chat with me. Now let us find the closures of the specified one. The A closure is telling you here A, B, C. You put those attributes here, and B closure is telling you B, A, C. Put those attributes here, and AB closure is also B, A, C. Put them there. Now here, this side I am calculating B closure, that is also ABC. C closure is only C, and BC closure is ABC. Now you observe carefully. We want to check membership testing. What is the membership testing is, from the arrived attributes after computation of closures, some attributes are not belongs to AB. Therefore, this C I can eliminate as it is not belongs to AB. This C I can eliminate This C I can eliminate. As far as this, only I need to maintain BC attributes. You can eliminate A, you can eliminate A here. After elimination, what are we going to do? We are going to check if these three dependencies are implied by our decomposed tables or not. The first one is A implies B. It is implying like this. A is giving you B here. And the second one is B to A. That one leave it. We will final with this dependency only. And A to C is solved or not. So how A to C can be solved here? Like this I can solve. A gives B from the first relation. A gives B union B gives C. Please observe. Union B gives C. Then we understand that A implies C. Therefore, A implies C there. So, the A to B is satisfied and A to C is satisfied. What about B to A? We have to check it. How to check B to A? Like this. You please observe here. The B to A, B implies A here. And therefore, this is also satisfied. So finally, from this example, all the given functional dependencies are available in your G. G is implied your F. Therefore, we will call it is dependency result. Okay friends, this is a simple example. Let us go toughest one like this. Now there are two decompositions are mentioned. We want to check whether decomposition is preserved or not. As far as this concern, write your F. The F is nothing but AB tends to C union C tends to A union A tends to D. And as far as your G concern, you need to bring them, that is ABC closures union BD closures. There is a one trick. The trick is like this. Whenever you have ABC functional dependencies are there together as ABC in one of your subrelation, then automatically this ABC will give you 100% a production called AB tends to C. No doubt in that. Because AB tends to C, if you combine those three attributes, you will get ABC only. So that ABC is available in your R1. Therefore, this is DP as far as this production concern. What about CA? CA, if you combine C and A together, you will get CA only. So C tends to A. If I am combining them, the CA together is available in R1 and so this is also satisfied. So CA is also available here only. What about A to D? So A is in R1 and D is in R2. Now we need to cross check before you say that whether it is DP or not DP. So let me find now A closer whether it is giving you D or not. So this and this is proved. Now I am finding A closer from your first relation as A is belongs to your first decomposed table only. So the A closer is giving you, please observe friends, A will give you D only. Nothing else you can map. You want to have C, there is a requirement of AB. You want to have A, there is a requirement of C. As I do not have those combinations, then you can leave it like this. Union So come here. Now I'm going to find a B closer and D closer. So B closer is only B and D closer is only D, and one more closer is left, that is a BD closer, which is nothing but B and D. Now we want to prove this dependency is proved or not. Let us cross check like this. How I am cross checking? This D you have to eliminate as it is not a member to your ABC. So it can give you only what, friends? A tends to A only. But you want to prove A tends to D, then it is not possible in that case, because this will give you D to D only. This will give you B to B only. This will give you B to D only. Therefore, this A unable to implies D attribute even though we are performing union operation between them. Therefore, in that case, A tends to D is not possible to imply, hence we are calling this is as not DP. Because AB tends to C is available in R1 and B to D, we already computed here B to D as it is belongs to this, and C to A, we already proved C to A, but only the problem with A to D. So A to D we cannot able to prove with this. That's why it is not DP. You come to this question now. So ABCD is R1, which means this is the responsible for many kind of combinations. What are the combination? A closer, B closer, C closer, D closer, AB closer, and BC closer, dot dot dot, many closures you can write till ABCD closures. So this A tends to BC is available here only. So we will write here that A tends to BC belongs to R1 and C tends to DE. There is a problem we will look at, and D tends to E we want to observe. D to E belongs to R2. And now the C RHS can be decomposed as C to D and C to E using union at decomposition rule. So we want to cross check this CD is implied or not. As CD, if you combine C comma D, the C comma D attributes are available in your R1, and so we will confirm this is belongs to R1. But the problem with only C to E, we want to identify whether could we able to preserve or not. So in that case, I am going to calculate C closure for this. The C closure is giving you CDE here. So this C closure I am calculating from R1 side. Please observe, I am calculating from R1 side these closures. So R1 is ABCD. So E is not there with me. You cancel that E. Only you will get C to C and only you will get C to D. Now we want to prove the closures for D and E here. If you find a D closure, the D closure is DE. As I am finding from R2, these two attributes, R2 is nothing but DE only, like this. So we want to maintain these two attributes. Now using union between them, you will understand C gives D and D gives E. So finally, you will get the concept of C gives you E. So therefore, C gives to E is also proved. C gives to D is also proved, and all are proved, hence we will confirm it is dependency preserved. Well friends, please observe carefully the lecture. Next question is like this. This is one of your previous GATE question. That is, the R is given with PQRS and R1 is a PQ and R2 is RS and given functional dependency is P tends to Q. He is asking a rule such that R1 intersection R2 is equal to 5. So the theorem 2 or theorem 3 is talking this lossy join. What is theorem 2 and theorem 3 of lossless join concern? There is a need of what? Common column is a mandatory. He said that between relation 1 and relation 2 there is no common. Whenever there is no common, then it is a what? Lossy join. We already proved. But you observe friends, we also want to prove whether it is preserved or not. The only one functional dependency is given, that is what? P tends to Q, and this P tends to Q. This is for LLJ test, and this is for DP test, that your P tends to Q belongs to which decomposition friends? R1. Hence, it is preserved. So finally, we will come to know that it is a lossy join and dependency preserving. Both are satisfying. So lossy join means what? It is a no lossless join and it is preserving what? Dependencies. Hence your option is C in that case. It is a lossy join. Lossy join means what? It's not a lossless join, but dependency is preserved, hence it is a dependency preserving. As some are chatting with me that it is not dependency preserving, but it's wrong. Why? The P tends to Q is implied in R1 itself. So we don't talk about another dependencies as it is not given, hence it is DP in that case. Okay friends? Any doubt, chat with me there. Please chat. If no doubt, give me a thumb. Any doubt? Yeah. Okay, fine. So you understand? Now P tends to Q is belongs to R1. Hence, it is a dependency preserved. This is the trickiness in this question. So come to next question. Now here, he asked both the properties. The DP as well as LLJ is proved or not. Now let us check LLJ condition. There is a straightaway condition. What is that? R1 intersection R2. If it is equal to pi, then it is a lossy join. We know. As far as given decomposition concern, AB is given and CD is given. As there is no common between them, hence it is a what? Lossy join. So look at the option we got, it is a not a lossless join. But what about DP? Is it preserved or not? Let us check dependency preservation here. What is a dependency preservation? A tends to B belongs to R1 and C tends to D belongs to R2. Therefore, it is dependency preserved. So option C correct. It is DP but not a lossless join. Yeah. Come to next question. So there are three decompositions are mentioned like this, namely A, B, B, C, C, D. Now we go for solution for lossless join. So take the table with the four attributes A, B, C, D, and three decompositions are mentioned. The decomposition R1 and R2 and R3. Now we are going to mark in the corresponding set of attributes. So AB here, BC here, and CD here. So after posting them, we want to apply functional dependencies A to B. As A is not a common in 1, 2 and 1, 3 and 2, 3, I cannot apply this right now. So I can apply B tends to C. Wherever B is a common, I can apply C value. Now I can apply C to D too. Wherever C is a common, I can apply in D. This is giving you R. So we will prove it is a what? LLJ. Now we also want to prove whether it is DP or not. There is a trick. What is the trick, friends? The trick is, or a shortcut you may feel, the trick like this. Whenever you have cycle of decompositions like this, see, A gives B, B gives C, C gives D, and D gives A. That means every LHS closure like A closure and B closure and others closure C closure and other closure D closure, all are giving you all the attributes of your R. So whenever there are cycle of dependencies are given like that, it is automatically proved dependency preservation. You need not check any kind of algorithm in order to prove this. Therefore, the answer is DP and lossless join. Now come to the next one. This is one of the famous question of the previous GATE examination, very tricky. Now we ask both the properties. I am checking first lossless join. The attributes are LM and OP, and we are going to post the decomposite attributes there. The first one is LMNP, and the second one is MO. Now we want to apply the functional dependencies. Let us apply M to O. Wherever M is a common, I am applying O. Just after applying first dependency, I got see that all the attributes of the given R is just implied by R1 only, hence it is lossless join. Now we want to prove dependency preservation also. How to prove dependency preservation? Let us prove here. First, M tends to O. This is belongs to R2. And next, P tends to L. It is belongs to R1. And next, L tends to M, belongs to R1. Next, L tends to N, belongs to R1. The only one is missed. That is what? There is a need of the combination of NO in a single table must be available. But in R1, if you observe, I could get LM or MN or NP or LN or LP. Any other combination I will get. either from L, M and P, but I cannot get NO combination together in either R1 or in R2. Therefore, what do we understand here? You cannot find such combination that NO at the LHS, then NO tends to P cannot be implied. So we will write here that we cannot get NO combination from there. Therefore, NO to P is not possible. From this, we prove that it is not dependency preserved. Okay, friends? Any doubt, please post in the chat box. Come to the next question like this. There are three decompositions are mentioned and we want to prove LLJ. So LLJ, four attributes, namely ABCD, and three decompositions, AB one decomposition, BC another decomposition, BD another decomposition. So we want to apply A tends to B. So as A is not a common in R1 R2 or R1 R3 or R2 R3, we cannot apply that A tends to B production here. So we will try to apply B tends to C here. So as B is a common in all the three places, wherever B is a common, you feel it's dependent, that is a C value here. Okay, now this is over. Now come to C tends to D. Wherever C is a common, I can fill D value. Therefore, this itself is giving you your R, hence it is LLJ. Now, we want to prove dependency preservation carefully. So how to prove the dependency preservation? That your first dependency A to B is available in R1 and B to C is available in R2 and D to B is available in R3. Only one is left. C tends to D. We have to check. Why we have to check? Because C is available in R2 and D is available in R3. So you need to have closures for them. Now I am finding from R2 concern C closure, as R2 has BC attributes. So the C closure is CDB So C closure is CDB union. I am trying to do with R3 closures, namely BD. So here we want to find a production that C tends to D only. You observe carefully. As D is not there in R2, remove this D from there. So we are going to cross check like this. C tends to B. Is there any production which can able to provide D value using transitivity? So whether B implies D or not, we are cross checking. So here also I am finding a B closure. The B closure from this is BCD. So cancel the C value as C is not with you. Now you see C gives B and B gives D. Therefore C gives D to you. How did we get? Please understand. We are getting like this. This production we got like this, that C tends to B union, B tends to D. You got this production, C tends to D. Hence we understand it is a DP as well as lossless join. And now let us look at into another question like this. Now you see there are some set of functional dependencies are given like QR to S, R to P, S to Q, and this is your original relation X, which is decomposed into two schemas Y and Z, and one decomposition is a PR, another decomposition is a QRS. We want to identify whether it is a lossy join or lossless join, DP or not dependency prism. Now I am checking LLJ here. So as far as given concern, there are four attributes are mentioned, namely PQRS. Now write the decompositions over there. One is a PR, the other one is URS. Now you see the first functional dependency is possible to apply or not. QR tends to S. As QR is not common, then I cannot apply this production right now. Let us move on to second production, that is R tends to P there. Now I can apply R tends to P wherever R is a common. I can apply P value. So this row is giving you R, and so we confirm it is lossless join. Now you look at dependency preservation concern. What is the dependency preservation concern? There are three dependencies given by F we want to prove in Y and Z, right? So I am writing here QR tends to S is belongs to Z. It is implied. R tends to P belongs to Y. Belongs to Y, and it is also implied. And next one, S tends to Q, it is also available in Z, and it is implied. Finally it is DP as well as LLJ. Well friends, any doubts you please type in chat box. Come to the very important question. This is, so there are four attributes are there in the relation R using the following dependencies, and he is asking which of the following is best decomposition. This is a very important question and very tough to solve, but let us use our shortcut tricks to prove in easier manner. Ready? Now here, in order to prove lossless join best decomposition, whenever he say you have to prove LLJ, you also have to prove attribute preserved, you also have to prove dependency preserved. You need to preserve all the three to prove that decomposition is the best. Right? Now it's in order to prove attribute preserved and lossless join and dependency preserved, what are required? Decompositions are required. Decompositions are required. But no decompositions you find in the question. There are no decompositions, only dependencies are mentioned. And what is the trick? That here only. What is that? I am checking option A. Option A is A to B and B to CD, which means there are two decompositions. One decomposition by name, combine those two, that's it, AB. And the second decomposition, combine the above, BCD. Very simple technique. Now I combine AB together, which is nothing but R1. I combine BCD together, which is nothing but R2. That means whenever decompositions are not given to you, you can consider each functional dependency as one of your decomposition. Okay, friends. Now you see LLJ is possible or not on your R. Your R is with A, B, C, D. And there are two decompositions, namely how I merged in the same way AB and BCD. Now I can apply A tends to B or not. Right now we cannot apply A tends to B where A is not a common. Now let us apply B tends to CD. As B is a common, now B gives you C and B also will give you D. This itself is saying that it is lossless join. Okay, the option A gives you lossless join. Now we want to prove whether it is DP or not. Obviously it is DP. Why? Because this A tends to B is belongs to R1 and B tends to CD is belongs to R2. Hence it is DP also. How it is DP, friends? Very simple. This B tends to CD is available here. And this A tends to B is available here. Hence, the option A is correct. It is attribute preserved. All attributes are available. Also, it is a lossless join. Also, it is a dependency preserved. Okay, friends. Now, let us check A to B, B to C, C to D. A to B, B to C, C to D from your R of A, B, C, D. Clear. Now decompositions, you can tell me what is R1, straight away merge them. What is R2, straight away merge them. What is R3? Straight away merge them. These are the decompositions. Now from this you can easily prove DP is satisfied. Why? A to B in R1, B to C is in R2, C to D is in R3, hence it is dependency preserved. You need to cross check only LLJ. Now I am checking LLJ here. There are 4 attributes on your R, A, B, C, D, and 3 decompositions. Mark them and post the respective values there. One decomposition AB, other decomposition BC, other decomposition CD. Okay friends, now we start apply A to B. Right now A to B is not possible. We start apply B to C. As B is a common in 1 and 2, I can apply this. This is done. And C to D, as C is a common, I can fill this. This is giving you R. Hence it is LJ2. Therefore, option B is also best decomposition. What about option C? AB to C and C to AD. AB to C and C to AD. As usually, you know how to put the decompositions. R1 merge it, R2 merge it. Now it's by default satisfy DP because DP is satisfied as AB tends to C belongs to R1 and C tends to AD belongs to R2. You need to prove only what? LLJ. There are 4 attributes in your R, namely ABCD. Put the decompositions. One is ABC, the other one CAD. Okay. Now you start apply functional dependency AB to C. AB is not common. I cannot apply. This is not possible to apply. C to AD. Wherever C is a common, I can get A value as well as D value. This is giving you your R, and it is LLJ. Therefore, the option C is also correct. What about option D? Observe friends carefully. Option D. Option D is given with A tends to BC. Now you tell me, is it attribute preserved or not? It's no. Why no? Because your R is ABCD, but R1 is ABC. So in this case, D attribute is missed. Yes, D attribute is missed. You're right, Jaya. D attribute is missed. Then I can say that it is not attribute preserved. When it is not attribute preserved, that's it. We will prove that option D is a what? Not best decomposition. This is how to prove, friends, lossless join and dependency preservation. So last question of the today's session is this. Consider relation STUV. Which of the following are best decomposition? Same question like the previous. As I told you, let us check option 1. What is that? R1 ST, R2 TUV. You see that dependency preservation is satisfied, those two productions, and we are going to cross check LLJ. The table consists of 4 attributes here, and I am going to mark them in first decomposition as S and T, second decomposition TUV. And I will start apply functional dependency S tends to T. Here S is not a common in 1 and 2. This is your decomposition 1 and this is decomposition 2. Therefore, S tends to T is not possible to apply. What about T2UV? It's possible. Wherever T is a common, I can fill U value and V value. This will give you R. Hence it is lossless join. We have to check the second one, ST2U, U2V. This is option 2. Your first decomposition is R1, STU, merge it. And second decomposition, UV. This is a merging rule. Whenever decompositions are not mentioned, you can merge them. Now DP is satisfied. ST tends to U is satisfied here. U tends to V is satisfied here. You need to prove only lossless join. How to prove? Your S consists of STUV, two decompositions, namely STU and UV. So we cannot apply ST tends to U functional dependency. Therefore, I cannot fill ST tends to U, but I can fill U tends to V. Wherever U is a common, I will fill it this. Hence it is LLJ. Therefore, both satisfied. Now let us look at third one, ST, S2 TU, U2 V. U2V. So friends, this is your R1 STU, this is your R2 UV, and I am checking right now option 3. It is by default dependency preservation is proved. This is and this is, because this production belongs to this and this production is belongs to this, as we constructed from the production only. That's why DP is satisfied. Now LLJ only we want to check. STUV. So first is STU, second is U tends to V. So I cannot apply S tends to TU property as S is not a common in R1 and R2. But let us check. U2V is possible. Yes. And this will give you R, and it is also proved LLJ. And only one option is left. That is ST2U, V and U2S. ST tends to U, V and U to S. This is your option 4. So your decompositions are STUV is a straight away single table. Automatically all will satisfy, need not worry. But you want me to prove, I will prove. This is R2, US, DP is proved here, DP is proved. Now only you have to prove LLJ. So first one is itself STUV only, very simple. This is giving you what? R, and it is also what? LLJ. So finally, what do we understand, friends? We understand that all are best decompositions. When they all proved best decompositions, when AP should satisfy, LLJ should satisfy, and dependency preservation should satisfy, then only we will call that it is a what? Best decomposition. That's it, friends. This is what is the end of decomposition topic. So decomposition is nothing but if there is any redundancies existed in the given relation, it may leads to inconsistency and data dependency problems and further anomalies too. In order to avoid those problems, there is a need to split your table into multiple tables. And after splitting, you have to be very cautious that it is best decomposition or not. The best decomposition is talking with AP, LLJ, and with DP. So stay tuned to Unacademy and my YouTube lectures. Morning, tomorrow's session is minimal covers, and evening special class is examples on minimal covers. Stay tuned to us and share these videos to all your friends and subscribe, take a subscription, use my subscription code to take the full course Sankara, then you will get 10% off. Thank you very much. In tomorrow's session, we will meet.